In this lesson, we examine the functions and operations of the bleed air system. Bleed air can be provided by the APU, ground air, or engines. The bleed air system supplies engine bleed air for air conditioning and pressurization, wing and engine anti-ice, engine start, cargo heat, the air-driven hydraulic pump or ADP, thrust reversers, and the pressurization of the hydraulic reservoirs. Bleed air controls and indicators are on the overhead panel. The controls and flow lines are arranged in a simplified schematic. Air flows through the left, right, and center bleed air ducts. The engines, APU, and ground air can supply pressure to the ducts. The left and right isolation switches are used to isolate the left and right air sources during normal operation. The center isolation switch controls the bleed air supply to and from the center duct. This switch is normally on, positioning the center isolation valve open. When the switch is on, a white flow bar displays in the switch. When the switch is off, an amber valve light displays in the switch. The pressure gauge displays bleed air pressure in the left and right ducts. Engine bleed air valves are automatically controlled when their respective bleed air switches are in the on position. Off displays in the switch until after engine start, even though the switch is in the on position. All engine, APU, and isolation switches are normally in the on position for engine start. The left and right engine bleed air off lights illuminate, indicating the engine bleed air valves are closed. When the APU is started, the APU bleed air valve opens and the center duct is pressurized. The valve light illuminates momentarily as the valve opens. The center duct is now pressurized. With the left and right isolation valves open, the left and right ducts are also pressurized by the APU. Position the right engine start selector to ground. The start valve opens, providing air to the starter. After the engine starts, the start valve automatically closes. Shortly after the engine reaches idle speed, sufficient bleed air is available to open the engine bleed valve. When the engine bleed valve opens, the APU bleed valve is automatically commanded closed regardless of the APU bleed valve switch position. Note, the valve light illuminates as the APU bleed valve closes. Positioning the start selector for the second engine to ground automatically closes the first engine bleed valve, opens the APU bleed valve to pressurize the ducts, and opens the start valve. Start the left engine. Again, notice after the second engine reaches idle, the APU bleed valve is automatically commanded closed. Once both engines are running, the isolation valves are closed. Push the left and right isolation switches now to close the isolation valves. Continue. A ground air source may also be used for engine start. Two ground pneumatic connectors supply air to the left duct. To provide sufficient airflow for air conditioning and engine starting, the left and right isolation switches are positioned on. Pneumatics are now available to all systems for engine start. Now, let's see how the system operates when the engines are running. Engine bleed air comes from either the high-pressure or low-pressure engine compressor sections. During low engine thrust, the high-pressure shutoff valve is open, allowing high-pressure air to power the system. As thrust is increased, the high-pressure shutoff valve automatically closes and the low-pressure section provides the air. After engine shutdown, the isolation valves must be in the on position to allow the APU or ground air to pressurize the system. Open the isolation valves. Continue. Now, let's discuss non-normal indications of the system. The APU bleed valve advisory message indicates the valve position disagrees with the commanded position. Here, the APU bleed valve is commanded open, but the valve is closed. The left or right bleed isolation valve advisory message and associated valve light indicate the valve position disagrees with the commanded position. The left or right engine bleed off advisory message and the engine bleed off light indicate the engine bleed air valve is closed and there is no flow of bleed air from the engine. When the left or right engine bleed overheat advisory ICAS message displays, the engine bleed air overheat light indicates engine bleed air temperature is excessive. If an overheat condition occurs, the engine bleed valve automatically closes. When the bleed air temperature cools to a normal level, the bleed air system can be reset. The system can be reset by selecting the engine bleed air switch off, then on. Reset the right engine bleed system. The ICAS message is removed and the off light extinguishes, allowing the system to operate normally. The left or right engine HPSOV caution message and the associated bleed light indicate the high-pressure shutoff valve is open when commanded closed. The left or right engine PRV caution message and the associated bleed light indicate the pressure regulating valve is open when commanded closed or when engine bleed pressure is high. When the system detects a bleed air leak, the ICAS caution message left or right bleed duct leak displays. The associated duct leak light also illuminates. The engine bleed air switch and the isolation switch on the affected side must be placed in the off position. The wing anti-ice selector should be selected off to prevent asymmetrical ice buildup on the wings. When the duct cools, the caution message cancels and the duct leak light extinguishes. If the left or right duct leak light remains illuminated and does not extinguish after the bleed source is turned off, a leak exists between the left and right isolation valves. The body duct leak message and duct leak light indicate that there is a leak along the center pneumatic duct. The controls to operate the air conditioning system are located on the overhead panel. The compartment temperature indicators are located directly above the air conditioning control panel. The left and right ducts of the pneumatic system supply air to the left and right air conditioning packs. The pack control selectors control the pneumatically actuated pack valves. The pack control selectors are used to select automatic pack operation. Rotate the left pack control selector to the auto position. Now rotate the right pack control selector to auto. When the valves are open, bleed air flows into the packs for conditioning, then into the mix manifold for distribution to the cabin and flight deck. In auto mode, pack output temperature is commanded by the pack controllers. Each pack valve has a normal and a high flow position. The valve opens for high flow when a pack is required to supply additional air. High flow occurs automatically and does not require crew action. The pack high flow system automatically provides higher than normal airflow for ground operation when the APU or ground source supplies air for air conditioning. While in flight, the high flow system activates when one pack is off, or when a recirculation fan is inoperative. The pack high flow system is inhibited when wing anti-ice is on and only one engine is supplying bleed air, when an engine is inoperative, when the flaps are extended beyond position 1, or when the aft cargo fire system is armed. Now let's look at temperature control. The compartment temperature controls are used to regulate cabin and flight deck temperatures. When auto is the selected pack controller mode, temperature control is automatic within each zone in the range from 18 degrees C, full cool, to 30 degrees C, full warm. With the pack selector in the standby mode, pack output temperature is determined by the three positions of the pack selector: normal, full cold, or full warm. Compartment control indicators display the actual temperature in each cabin. The flight deck temperature selector control can be operated in either the auto or manual mode. In manual, the selector is spring-loaded to the 6 o'clock position. In manual, moving the selector control towards cool or warm moves the zone trim air valve, allowing the trim air to adjust the flight deck temperature. The compartment temperature controls provide temperature demand signals to the zone temperature controller. The controller compares demanded temperatures to the actual temperatures in each compartment. The controller then determines the coldest temperature required in any of the operating zones, then passes that signal to the automatic pack controllers. The pack controllers command the packs to the demand temperature. Once the coldest required temperature is being provided by the packs, the trim air system supplies bleed air to adjust the temperature in the compartments requiring a warmer temperature. The zone temperature controller commands the trim air system to add hot bleed air as required to each compartment's conditioned air distribution ducting. The left and right recirculation fans are used to circulate discharged air from the flight deck and passenger cabin back into the mix manifold for distribution. Air is recirculated to maintain the desired level of passenger cabin ventilation while minimizing the use of bleed air. In auto, the pack is automatically commanded by the autocontroller to provide the coldest compartment temperature. The trim air and recirculation fan switches are on, and the compartment temperature controls are set to the desired position. The panel is now configured for normal operation. Foot and shoulder supplemental heat systems are provided for the captain and the first officer. Electric heaters provide additional heat to the conditioned airflow being distributed to the shoulder area. The foot and shoulder supplemental heat systems operate only when the airplane is in the air. Now let's look at the non-normal conditions. We'll begin with pack control faults. Anytime a pack valve closes, whether due to loss of pneumatic actuation pressure or system shutdown, the pack off message and pack off light will illuminate. If the pack valve closed due to loss of pressure, restoring pressure will cause the pack valve to open. The pack off light and message will extinguish. A pack temp message and in-op light indicate either a pack controller fault or high pack outlet temperature. If a pack controller fails, the pack will remain at its last commanded output temperature. Select Standby Normal on the left pack controller. After selecting Standby Normal and the pack temp message and the in-op light extinguish, a controller fault is confirmed. Continue to operate the pack with the standby controller. However, if the pack temp message and the in-op light remain illuminated after selecting the standby controller, wait 5 minutes and reset the pack by pushing the pack reset switch. When the pack is reset, the advisory message disappears and the in-op light extinguishes. The pack returns to the selected control mode. If the in-op light does not extinguish or re-illuminates, a pack failure is confirmed. Turn the pack off for the remainder of the flight. The ICAS message Left Pack Off shows and the Pack Off annunciator illuminates. If a pack fault causes outlet temperature to become excessive, system protection will command the pack to full cool output. The pack temp message and the in-op light will illuminate. Pack output will remain full cool until the pack cools and the pack reset switch is pushed. Push the left pack reset switch now to reset the pack. If the pack resets, the advisory message disappears and the in-op light extinguishes. The pack returns to the selected control mode. If the pack off light illuminates together with the in-op light, a pack trip due to an internal pack overheat is indicated. After the temperature has cooled below the overheat level, the pack may be reset by pushing the pack reset switch. The ICAS messages Left Pack Temp and Left Pack Off blank. The in-op and pack off lights for the left pack extinguish. Now let's look at trim air system non-normals. With the trim air switch off, the trim air valve is closed. This is indicated by a trim air message and a trim air off light. Since the trim air system is disabled, the zone temperature controller cannot trim the temperature in each compartment. This is indicated by the cabin compartment and flight deck temperature messages and in-op lights. With the trim air switch off, the zone temperature controller sends an inoperative signal to the pack controllers. The packs provide a 24 degrees Celsius cabin temperature. If the zone temperature controller has failed, the effect is the same as selecting the trim air system off, except there will be no trim air message or trim air off light. A single cabin temperature message and associated in-up light could indicate a fault in the zone temperature controller or a zone supply duct overheat. Trim air to that compartment should be shut off. When a zone is selected off, the zone temperature controller determines temperature requirements based only on the remaining zones. Now let's look at the recirculation system. The in-op light and recirculation fan message illuminate when the recirculation fan switch is in the off position. If the in-op light and the recirculation fan message illuminate with the recirculation fan switch in the on position, the fan has failed, has load shed, or is inhibited. The recirculation fans are inhibited when a cargo fire switch is in the armed position. The equipment cooling controls and indicators are located on the overhead panel. The forward equipment cooling system supplies cooling air for the flight deck instrument panels and the forward electrical-electronic compartment. Equipment cooling is accomplished by either recirculating air through the flight deck instrument panels and forward E&E compartment, or by porting the air through the overboard exhaust valve. The equipment cooling is normally operated in the auto mode. On the ground, engine operation, pack operation, air-ground logic, airplane skin temperature, and ambient temperature are all factors that determine system configuration. A supply and exhaust fan either recirculate the cooling air back through the system or port it overboard. In flight, only the bypass valve is open and the exhaust fan operates. If the exhaust fan fails, the supply fan automatically switches on. The other two modes of the equipment cooling system, standby and override, are used under specific non-normal conditions. The standby mode is used in response to an overheat condition or valve disagreement. In the standby mode, all valves close except the bypass valve. On the ground, both fans operate, but in flight, only the supply fan operates. However, if the supply fan should fail, the exhaust fan will automatically operate. The override mode is used when overheating can't be corrected by the standby mode, or if smoke is detected in the system. In the override mode, all valves are closed except for the smoke override valve. And both fans turn off. Conditioned air is diverted into the system, and differential pressure causes reverse airflow through the system. Lights on the equipment cooling panel and the associated ICAS advisory and caution messages identify non-normal cooling operation. The valve light illuminates and forward equipment valve ICAS message is displayed when any of the valves are not in their signaled position. Selecting Standby provides an alternate command to reconfigure the system for recirculating the air back through the system. The overheat light and forward equipment overheat message appear when low airflow or high temperature is sensed. Selecting Standby will reconfigure the system and may correct the overheat condition. In the standby mode, the overheat light and message are extinguished and inhibited for 5 minutes to provide a cooling period. If the overheat condition is not corrected at the end of the 5 minutes, the overheat light illuminates. Override deactivates the overheat light, changes the source of cooling air, and vents the air overboard through the smoke override valve. The smoke light and forward equipment smoke message display when smoke is detected in the forward equipment cooling ducts. Selecting the override mode allows conditioned air to be drawn through the system by differential pressure and exhausted overboard. As the smoke detector is away from the overboard airflow, it may take a while for the light to extinguish. As the smoke detector is away from the overboard airflow, it may take a while for the light to extinguish. The No Cooling Light and Forward Equipment Cooling Caution message display if no cooling airflow is sensed when the override mode is selected. Should the No Cooling Light illuminate 1 minute after selecting Override, Standby should be selected. Standby ensures equipment cooling, however the smoke will be removed with the normal airplane exhaust air. Normally, one of 2 exhaust fans cool the aft compartment by drawing air through the aft compartment and discharging it near the outflow valve. If the operating fan fails, the alternate fan automatically starts. Heat for the forward, aft, and bulk cargo compartments is provided by 2 sources. Warm cabin discharge air flows around the cargo compartments before being recirculated or dumped overboard. Additionally, the cargo heat system provides hot bleed air under the cargo compartment floor. Controls for this system are located on the flight deck. Controls for the forward, aft, and bulk cargo heat are located on the overhead panel. And the accessory panel behind the first officer's seat. Each overhead switch controls a heat control valve and a shutoff valve in each cargo compartment. When a switch is on, the shutoff valve is commanded open, and the heat control valve automatically maintains compartment temperature above approximately 7 degrees Celsius, 45 degrees Fahrenheit. Continue. Now let's look at the bulk cargo heat selector. Heating and ventilation of the bulk cargo compartment is controlled by the bulk cargo heat selector. With the selector in normal, heating works the same as the other compartments. In the vent position, the heat control valve will automatically maintain a temperature above approximately 65 degrees Fahrenheit, 18 degrees Celsius. To provide air circulation in the compartment, vent also turns on a vent fan to draw cabin discharge air into the compartment. Next, we'll look at system non-normals. When a cargo compartment overheat light illuminates and the associated cargo heat ICAS message is displayed, the compartment temperature is above the standard control range. The system responds to the overheat by automatically closing the shutoff valve. When the compartment cools to a temperature below the overheat setting, the system automatically resets. The overheat light extinguishes. The ICAS message is removed, and the shutoff valve reopens. If heating is required, the heat control valve will open. The pressurization system controls cabin altitude by regulating the discharge of conditioned air from the cabin. In this lesson, we examine the functions and operation of the pressurization system. You will learn how the cabin is pressurized automatically and manually, and how to identify non-normal conditions. The pressurization system controls and indicators are on the overhead panel. There are two cabin altitude warning lights. One cabin altitude warning light is on the equipment cooling panel located directly below the cabin altitude indicators. The other cabin altitude warning light is on the center forward panel. Both lights illuminate for cabin altitude warning conditions. Normally, cabin altitude is controlled automatically. During non-normal conditions, the system is operated manually. Let's turn our attention to the automatic system. Two identical systems identified as Auto 1 and Auto 2 provide cabin pressure control for normal operation. When either Auto 1 or Auto 2 are selected, the auto cabin altitude controllers receive ambient pressure data in conjunction with the selected cabin auto rate, takeoff altitude, and indicated landing altitude to establish the cabin pressurization schedule. The automatic mode controls cabin pressurization by adjusting the amount of conditioned cabin air discharged through the outflow valve. Should the selected autocontroller fail, pressurization control is automatically switched to the other controller. If one autocontroller fails, the other autocontroller accepts control. The auto rate control establishes the limit for the cabin rate of change. At index, the rate of climb is limited to 500 feet per minute. The rate of descent limit is 300 feet per minute. Actual rates of climb or descent of the cabin may be less. The landing altitude selector is used to set the landing airport elevation. And the landing altitude indicator displays the destination airport's altitude. During pre-flight, the altitude of the destination airport is set by rotating the landing altitude selector. The cabin differential pressure, cabin altimeter, and cabin rate of climb indicators are shown here. Let's observe the operation of the automatic system during a normal flight profile. The mode selector is positioned at Auto 1 or Auto 2, and the auto rate is at index. You must set the landing altitude of the destination airport. Touch the landing altitude selector to set the altitude to 1,240. When the engines are running, the cabin altitude descends slightly below the takeoff airport elevation. During climb, cabin altitude increases at a rate proportional to the rate of airplane climb until maximum differential pressure of 8.6 psi is reached at approximately 35,000 feet. Then, the cabin follows a climb schedule to maintain 8.6 psi differential. The system enters the cruise mode shortly after the airplane levels off. At that time, the cabin altitude controller compares the selected landing altitude with the scheduled cabin altitude and selects the higher of the two for the cabin. If a climb is required, the cabin climbs at 1/2 the selected rate. If a descent is required, the cabin descends at the auto rate setting. If the airplane climbs or descends by a significant amount, this will cause the system to re-enter the climb mode or enter the descent mode. When the airplane descends from the cruise altitude, the system enters into the descent mode. During descent, the cabin altitude decreases to slightly below the selected landing altitude to ensure a positive pressure on landing. The landing altitude barometric pressure comes from the captain's altimeter. The cabin is controlled to approximately 100 feet below the selected landing altitude. Upon touchdown, the controller signals the outflow valve to open to depressurize the airplane. If the cabin auto in-up caution message displays with the auto in-up light, both Auto 1 and Auto 2 cabin altitude controllers are inoperative. The outflow valve freezes in its last position until manual control is established. The light remains illuminated to indicate the status of the system. Let's turn our attention to the manual mode. When the cabin altitude mode selector is positioned to manual, the cabin altitude manual control is used to open and close the outflow valve. By holding the manual control towards climb or descend, the outflow valve moves to open or closed. Manual control uses DC power from the standby DC bus to position the outflow valve. Let's look at other non-normal indicators. If the cabin altitude exceeds 10,000 feet, the master warning light illuminates and the siren sounds. The cabin altitude lights illuminate and the cabin altitude warning message appears. The warning message and lights cancel when the cabin altitude descends below 8,500 feet. If the cabin altitude climbs above 11,000 feet in the auto mode, a pressure switch automatically commands the outflow valve to the full closed position. When the cabin altitude descends below 9,500 feet, normal operation of the outflow valve is restored. Cabin altitude warning lights remain on until cabin altitude descends below 8,500 feet. Positive pressure relief valves limit the maximum differential pressure. Negative pressure relief doors prevent ambient pressure from exceeding cabin pressure.